So Matt, welcome. And reading from your bio, you're extractive metallurgist. You were an extractive metallurgist working in base metal mining industry in the Australian desert and the Canadian Arctic. Sounds like an interesting mix of places to go to. And apparently it got you interested in extreme conditions and even wanted even more extreme conditions. So you're now headed for astrometallurgy and the moon and working in Australia, and back in Australia, I guess, working for the Australia's National Science Agency and specializing in resource extraction in space. So the floor is yours, and the air and ether and whatever you need.
That sounds like me. Thank you very much. Pleasure to be here. You can see the slides okay?
Yep, they look good.
Yes, maybe. Awesome. Yes, so thank you so much. Yeah, my name is Matt. I work for ISRU, which again is Australia's National Science Agency. And we have a team that works on ISRU, or Space Resource Utilization Technologies. I'll talk a little bit about them. We're going to talk today about astrometallurgy, and I guess specifically in relevance to lunar settlements and construction manufacturing activities on the moon. Of course, we do cover things out to Mars and such, but I'll focus on the moon today. CSIRO is, just make sure I can actually change the slides here. There we go. CSIRO is, as I mentioned, Australia's National Science Agency. We've got one of the largest research organizations in the world. We've got over 6,000 people at over 57 sites worldwide, which is pretty cool. And we don't just do space science. We do everything from animals and plants through to mining technologies, renewable energy, robotics. It's everything in between. One of the things that we kind of pride ourselves in is being able to put together teams to tackle big issues, and we pull in experts from any topic that you could possibly want. So as a general rule, we try and tackle topics that we think other people might not be able to, just because of the broad range of expertise that you might need in different areas. So for the ISRU team, we have people from everything from robotics to sensing and sensors through to actual, space launch systems and all this kind of stuff. So we have kind of a broad range of expertise in different areas that allow us to tackle some pretty fun challenges. And of course, ISRU is one of those challenges. I probably don't need to define specifically what ISRU is in this kind of context, but I will anyway, just to make sure we've got some basis there. We are talking about space in situ resource utilization. And I'll stress that because, as I mentioned, I come from the terrestrial mining industry, and ISRU has a subtly different meaning when you talk to terrestrial mining professionals. So I would caution you if you're trying to do that. They do have a preconceived idea of what ISRU is if you open with that. But of course, it's a buzzword that NASA's been using for quite a while in terms of this idea of using space native resources in space. And I've heard recently some really good comments. So we had the World Mining Congress a couple of weeks ago here in Australia, and we had a stream on future mining frontiers, which we kind of co-opted into space mining, which was quite fun. And one of the really good comments that came out of that was some mining professionals saying, hey, this sounds interesting, but do we need to? Because we've all seen the amazing launches by SpaceX, and we've seen some pretty cool rockets up and coming, SLS, for example, Starship, and even some smaller ones in Europe now. Do we need ISRU? Because surely at some point we're just going to get cheap enough for transport that it's going to be easier to just send things from Earth. And that is kind of true, apart from the fact that we have a significant energy limitation. So my fun fact that I use is that it takes the same amount of energy. This is not cost, this is just pure energy requirements. Same amount of energy to get from Earth to low Earth orbit, which is a couple of 100 kilometers up, as it does to get from the surface of the moon to low Earth orbit, which is a couple of 100,000 kilometers. So if we're launching the same rocket from Earth as we are from the moon, which we can maybe do these days with renewable rockets, it doesn't matter how good our rocketry technology gets, it will always be significantly cheaper to get anywhere in cislunar space or in the solar system if we're launching from the moon. So this idea of using space native resources, especially fuel, is really important for us and has been identified as by every major space agency in the world as being kind of critical for future space activities. So ISRU is a pretty broad thing to talk about, I suppose. We're talking everything from sensing and mapping all the way through to manufacturing and construction. And again, at CSIRO, we have people working on, pretty much every aspect of this supply chain. I'm going to be talking today about my my little niche area of astrometallurgy, which is this kind of mineral processing, resource extraction stages. And I'll explain a little bit about what those are and what it entails. We'll talk about some of the challenges that we encounter when trying to develop these processes for use in space. And then I'll go a little bit more in depth about some of the processes that we probably will be expecting to see in the future on the moon for resource extraction that might be kind of more relevant to the idea of building a lunar base. So when we're talking about astrometallurgy, we're talking about the kind of first stage, which is mineral processing, which we break down into comminution, which is particle size reduction, making things smaller, and classification, sorting those particles based on size. Beneficiation, which is the particle sorting itself, is where we're taking certain minerals and upgrading them, extracting certain metals. And then the resource extraction, which is the reduction and or separation. Now, not only metallurgists in industry, it's very much in the name, we deal with metals. However, it's not uncommon for metallurgists to also work on other resources such as silicon and coal and all sorts of other bits and pieces. So while we do tend to work on base metals, we do deal with kind of all resource processing in general. And in space, that's really important because there are other resources other than metals that we're probably even more interested in than we are with metals. Extractive metallurgy on Earth tends to be very energy hungry. It tends to require large surface areas in terms of plant size. And it's a pretty interesting and human intensive operation. And so while the basic principles are going to be the same in space in terms of how we separate materials out and what we do with them, like looking at their chemical and physical properties, it's going to look radically different in space because we can't afford to do that. So you mentioned I worked in the Australian desert. This is the processing plant that I was working on there in Broken Hill. Pretty cool place, and by cool place I mean extremely hot. We used to wear ice vests during the summer, which was pretty interesting. I hear you guys are having a heat wave at the moment, potentially over in Europe. So that was kind of our normal everyday summertime goodness in Broken Hill, which was lots of fun. And relatively extreme conditions, but we still had things like plenty of access to chemical reagents, plenty of humans, plenty of water. So it really flavors how you operate these processes. And while we'll be using similar ideas again in space, the processing plants are going to look radically different. And that's what I'm going to talk to you a little bit about today. The main reason that the processing plants are going to be different is the conditions in space. So obviously on the moon, we have some pretty extreme conditions, I'd say. Gravity being relatively low. My favorite YouTube binge is looking up NASA's astronauts falling over on the moon. I always thought that astronauts were, relatively competent people, but apparently they can't even walk particularly well. So I don't know, maybe just changing something as fundamental as gravity really affects how you can do basic things like walk. And of course, it's even more affecting our complicated chemical physical reduction processes. Human access, as I mentioned, severely limited. Water accessibility is a big one, and I'll explain why. But the fact that we don't really have much water, we do have water on the moon, but we're not going to be using it for processing. So that changes very much how we do these beneficiation mineral processing operations. Temperature, dust, all these things kind of play into how we need to be trying to do extraction on the moon. So let's step through. So comminution, I mentioned, is the first stage of mineral processing. Comminution is the art of taking a large rock and turning it into a smaller rock, which sounds pretty simple, but I can guarantee you it gets a little bit complicated sometimes. It's a pretty energy intensive process on Earth. It takes a lot of energy to crack rocks open. In fact, there's an interesting relationship between surface area. So as you take a small surface area and turn it into a larger surface area, you need almost a fixed amount of energy, which is pretty cool. But you can imagine when we're taking a 1-ton boulder and turning it into micron-sized pieces of dirt, we're requiring quite large amounts of energy. The idea of comminution is twofold. The first, we want it to be the material that we're working with to be in a more handleable state, right? So throwing around large boulders is kind of difficult, requires energy in and of itself. So we want to reduce it down to some sort of rock slurry, something that we can pour into tanks and that kind of thing, pump around. And the other thing that we're really going for is what we call liberation. So metals in rocks are found in the form of minerals. And what we would like is when we have all of these individual very small particles, we would like the minerals that we're looking for to be in what we call a monomineralic state. So there's not other things bound up in that particle. So when we separate them, we can quite easily make a detailed concentrate of that metal. That's what we're going for. So comminution processes are often targeting mineral liberation. What I've got up here is a diagram of particle size of lunar regolith samples. So this is returned lunar regolith samples from the Apollo missions. And you can see here that they've actually got quite a well-distributed but relatively fine particle size. The number that we often use in industry is the P80, or the 80% passing, which you can see on the left-hand side there. It's between about 200 to 300 microns, which is pretty small. And the average, or the P50, is around about 70-ish, 60 to 70 microns, which is a pretty fine material. This is slightly larger material than we would normally have in a comminution stage on Earth. But compared to boulders, it's very much a handleable material. So the argument is we probably don't need classical comminution. We don't need to crush this material down more. Unfortunately, while we would normally be going for particle liberation in these particles, that's not really the case in the lunar regolith. Regolith is formed by meteoric impact. It's something that we find all over the surface of the moon from about 2 to 15 meters in depth. So there's plenty of it there, but liberated the particles are not. There's lots of glassy content, they're quite jagged, and we have multi-mode particles, which is a shame, but it wouldn't really be worth it for us to try and break that material down more to try and liberate those materials. So probably what we're going to be doing is just using the lunar regolith. What you might see in future is basic particle size classification. So that would be removing large particles, say 1 millimeter and above, potentially removing finer particles like the really dusty stuff, because that's pretty nasty for its own reasons. And then just using that kind of middle band of particle sizes to then process. So that's kind of a good thing in the sense that we don't need all the energy we would normally associate with comminution. It's slightly bad in the sense that we're not going to have the particle liberation that we would normally like to see for our mineral processing step. But just a particle classification stage, it's much easier to operate, much easier to automate, and not going to require as many wear parts in the future. So that's nice. That takes us on to beneficiation. So beneficiation is the process of taking bulk material, separating out the minerals that we are targeting. And what we normally end up with is a concentrate stream and a waste stream. And I'm using air quotes there because obviously for a lunar settlement or space operation, we don't really want waste streams in that sense. So what we would probably end up with in terms of what we would call it rather than a waste stream would be a beneficiated or depleted product, because we would want to use that, right? We want to minimize handling material when we're in space, because it takes, again, a lot of energy and effort to be handling anything. So we would probably end up with a concentrate stream and then a depleted stream, so a stream depleted in, for example, iron, that we could then use to make ceramics or glass or, print structures, whatever it might be that you're interested in doing with that silicate material. We could use that elsewhere. Something that we're really targeting in space is this kind of idea of zero waste processing, circular economy, good recycling, all that kind of stuff. So not having waste streams is pretty important for that. But in terms of beneficiation, it is a waste stream in the sense that it's not what we're particularly targeting with our process. It's just what's left afterwards. The diagram I've got up here at the moment is most of the processing options available to us that we use in terrestrial processing. You can see the top there, which is kind of in white, is all of our wet processes. And the bottom bit I've highlighted in gray is the dry processes. And the reason that I've separated these out, as I mentioned, is because water is unfortunately not really going to be an option. So this is a challenge, right? In terrestrial processing, I used to, my expertise used to be in a process called froth flotation, which is pretty cool. Definitely look that up. We literally float rocks to separate them, which is a really fun process that was actually developed here in Australia many, many years ago and is used worldwide. It's really good, doesn't work in space, right? It requires buoyancy and it requires water, neither of which we have particularly much of on the moon. And this is a shame because, again, most of our processing options use water because, again, it's really prevalent on Earth and it's something that we're very used to using. It works really well. While there is water in the moon, and we will be going to, Shackleton Crater, that's the reason that NASA wants to go there, is because we think that there's volatile deposits. the volatiles themselves are worth more than any metal that we would be able to make using beneficiation processes. So it's not really an option to use that water in the process to extract metal. So we're probably, certainly at the moment, maybe in the distant future, we'll have enough water up there that we could start using it for things like this. But I would suggest that probably not. We're probably restricted to dry processing options. Even some of those dry processing options are probably not particularly good ones. So you can see a few pneumatic ideas there using air and compressed gases to process materials. We can do that. But again, when you're introducing compressed gases or pneumatic processes into this kind of processing flow sheet, we then have to recover those gases, and that adds a lot more process complexity and, again, energy requirements into the process, which is not ideal. So we're pretty restricted in the types of processes that we can use to concentrate minerals, which is a shame because we really do want to concentrate minerals. It makes our reduction stage, our final metal extraction stage, much more efficient if we can separate out that waste stream so we don't have to heat that up and spend energy on it. Luckily, we do dry processing on Earth. You can look up the mineral sands industry. We do things like electrostatic processing, magnetic processing, even particle size distribution and gravity processing that are all in a kind of dry state. It's a little bit esoteric. It's not something that people are used to using as much because water is so useful, but we do it. The one thing that you will notice, which is a bit of a challenge, is that the particle feed size for most of these dry processes is significantly shifted to the right in this figure, and that being larger particle sizes. And if you remember that I said that our P50, our average particle size of the lunar regolith, was around 60 to 70 microns, that is below the required feed size for a lot of these dry processing options, which is not great. What it means is that we have to do quite a lot of work to either modify these processes so they work in low gravity and with a finer feed particle size, or we just have to be a lot less harsh with our separation. So instead of trying to get these really nice concentrates that are like 80 to 90% of the mineral that we want, we can say, look, if we get even a 5 to 10% upgrade, it's still a win for us. And we can use processes like that. So beneficiation processes will exist in space. The economics are always in favor of these kinds of mineral processing, but it will look wildly different to what we do on Earth. So I'm, as an extractive metallurgist, used to working with massive processing plants that take up probably multiple times the size of what our lunar settlement is envisioned to look like. Processing won't look like that. It'll be very static, it will be dry, it will be relatively simple processes that give us just a little bit of an advantage in terms of the concentrate that we are working with, and our waste streams will probably be used in construction and such as well, rather than in terrestrial industry where we kind of just throw that out along with a lot of our chemicals and water that we're using. So it will exist, but it will look different. And the resource extraction stage is kind of the interesting one. Is the one I really love working on because it gets pretty crazy at times. I do specifically, as I mentioned, say resource extraction because something like water ice mining is probably still the purview of an astrometallurgist. Lots of work has been done on that, so we don't focus too much at the moment because we're kind of already waiting for test payloads to be sent up that do this kind of stuff. But the idea of creating ceramics and glass is also really important. As I mentioned, those waste streams will be used for those processes. But for now, we're going to focus on the metals, the interesting bits. Now, the idea of extracting specifically metals is weirdly new. Sci-fi for plenty of years have looked at construction in space, and obviously it would use metals for that. But in terms of actual research that's been done, metals haven't been a specific target for most of our history of looking into ISRU. That's predominantly because NASA has been interested in oxygen. Right? And oxygen obviously is pretty good for life support and is a rocket fuel oxidant. So there's good reasons for that. So a lot of these historical research processes have taken a bunch of different methods of extracting oxygen from regolith. Now, the fun idea is that if you're taking a metal oxide and you're taking the oxygen out, you are almost always producing a metal. So these processes and historic research has been looking at metal extraction, but it's been kind of a side product. Like, we also produce metal, which might be useful. Now, there is an extra step there that a lot of those studies have been missing, which is the phase separation. And I'm not going to go into that too much today, but that is one of the harder aspects of metallurgy is you could always make metals, but then you have to kind of separate out the metal from the rest of the junk that you don't want. And that can be interesting. So a lot of research has been done into the area of astrometallurgy, and I use, again, massive air quotes there, but it's only been the last 4 to 5 years where people have said, oh, maybe we should be specifically targeting metals. And yes, we do need to make sure that we extract all the oxygen that we get off using these processes, but we should probably put in the extra step of phase separation and really targeting metals and see if we can get pure usable construction materials for use in space. I can break these down. So not all of those processes are particularly optimized for use in space for obvious reasons. We have a plethora of options available to us, but not all of them are particularly useful. Some of them are a little complicated, and that's not something that we particularly want in space. There are 3 main areas that we can look at in terms of reduction technologies, or 3 main pathways. So when we're trying to produce a metal, all we need is energy. We need to provide energy to the system to break the oxygen off that oxide. And we can provide that energy in 3 states. We can use chemical potential energy, we can use electrical energy, and we can use thermal energy. Chemical potential energy is the one that we predominantly use on Earth. And the 2 options that are available to us that are most likely to be used in space in the future, so when we're looking at a lunar settlement, this is probably what we'll be looking at for metal extraction, would be carbothermal reduction and hydrogen reduction. Carbothermal reduction is obvious. That's the one that we use most on Earth. That's most of our metals on Earth using some sort of carbothermal process to produce them. Again, the reason we do that is because carbon is everywhere, and it's a very, very good way of producing metals. Is it optimized for use on the moon? Probably not. There's not much carbon up there, which means that we need to bring it all with us, and we need to resupply from Earth. But it is a very good process and useful. I can see a message here quickly. I'll come back to the messages a little bit later, maybe for some questions. So carbothermal reduction will work in space, and we will take it to the moon for CLIPS missions. It's not particularly optimized for use on the moon, but what it is optimized for is use on Mars. And since things like the Artemis missions are specifically looking at forward thinking to Mars, then carbothermal is a really good option for testing on the moon. Hydrogen reduction works, and it's a good technology in the sense that we have hydrogen native to the moon that we can use, so we don't necessarily need to resupply from Earth, which is good. But hydrogen is limited in its reduction potential, so we can only really reduce iron minerals, and even then only really a specific mineral called ilmenite, and we're only looking at a couple of percent reduction efficiency of regolith in bulk, which is kind of a problem, but it is a really nice demonstration of ISRU. There are alternate technologies that use hydrogen, like hydrogen plasma reduction, but they're a bit lower TRL. And so the initial test that we'll see on the moon for hydrogen reduction will be this just basic lower temperature hydrogen reduction. It'll work. I would suggest that in terms of actual extraction efficiency, it's probably not our best bet, but we will see it used. Again, it'll be tested as part of the CLIPS missions that NASA's sending up. Probably the more useful technology types and the ones that we'll see in more use in the future, I'm saying 10 to 50 years, will be the electrochemical processes. So we do use electrochemical processes on Earth. Aluminium, for example, is produced using the whole Haro process. That's pretty much all aluminium in the world is produced using that process. So it works pretty well. The ones to look out for in terms of space use are molten regolith electrolysis and solid electrolysis. So molten regolith electrolysis is quite literally taking regolith, melting it into a puddle, sticking electrodes in and passing electricity through, and you form oxygen at one end and liquid metal at the other end. That works pretty well. This would be my best bet. Minimal reagents required. You do need to replace the electrodes sometimes, unless you're spending ridiculous amounts on large platinum electrodes, which is probably not ideal. So there are some issues there. We do have a lot of technical issues in terms of fluid dynamics and viscosity and the mechanics of how we get the metals out of the cell, but it works pretty well and it's pretty simple. All we need is electrical energy and some time. So that's a pretty good option in terms of metal reduction or production technologies. And the other one being looked at is solid electrolysis. Solid electrolysis is a lower temperature process. It operates below the melting point, which is nice, more efficient in that sense. It does require normally a solution of some variety, so a molten salt or something like that. There's a lot of interest at the moment in Europe looking at molten salt solid electrolysis processes. And it's good because the extraction efficiency, especially of oxygen, is really high. So you can theoretically get almost 100% of the oxygen out of the regolith, which is good. It takes you a while, but that's something that's of significant interest. The downside is, again, you will have to resupply with this molten salt solution, and that can get a little bit complicated in terms of handling. The last option is thermal processing, and this is something that's relatively close to my heart. It's what I completed my PhD on. Thermal processing, pure thermal processing, is not something that we do on Earth. It's not energy efficient at all. The reason it's of interest in space is that it requires less energy to thermally dissociate things like rocks, and that is to literally vaporize them and make the oxygen and iron or metals separate from each other when you're operating in a vacuum. So the high vacuum conditions in space lower the energy requirements for thermal dissociation quite significantly, which is interesting. But because we don't use this technology on Earth, we don't really know what we're doing. So the technology readiness level of these thermal processes is extremely low. The advantage is, theoretically, you can use concentrated solar thermal energy, which would actually lower the electrical load on the process. So while it does require more energy in total, we don't have as much energy conversion processes, so we're not losing as much to those conversions. So it is actually a beneficial process. Probably what we will see is the use of concentrated solar thermal to heat these other chemical or electrochemical processes. Thermal processes, pure thermal processes, won't be tested anytime soon, but they will be tested in the future. And I'm talking, decades in the future, probably. This will be my best bet for like true sci-fi processing, but it's going to take us quite a while to get there in terms of the technology that we need to develop. If you're interested in more information on these topics, you can check out this publication. I think it was last year published. It's got way too much information. It's a slightly long document, but it goes through all the different conditions and how they affect these astrometallurgical processes. So if you're a sucker for pain, then do have a read through that. It's if I do say so, a pretty cool publication. It's got lots of information in there and goes through every single step in way too much detail. So you can just scan that QR code there. Or of course, please do reach out. I'd love to have a chat with you. And again, we have a team that works on kind of all aspects. So if you've got some projects that you're interested in, potential collaboration, etc., we're always interested in having a chat. Thank you very much.
Thank you, Matt. And we have some time left for a few questions, or at least one. Let's take Philip's first one. Are you referring to processes that are mostly continuous or discrete? A discrete process could be used in an industrial scale centrifuge.
Yeah, so it's an interesting debate. For the moment, we're looking at discrete. So continuous is not something that we normally need to consider until we're looking at bulk processing. So a small processing plant on Earth is talking hundreds of tons per hour. We will not have the capability to be doing that on the moon anytime soon. So for the most part, these will be discrete processes. You can use a centrifuge. Most centrifuges for processing use a fluidization medium of some variety. All right, so we would categorize those. Normally we would use water, obviously. There are pneumatic centrifuges, but if you just take regolith and spin it really hard in a vacuum, you won't get anywhere near as much separation as we would like to see. The other downside is that normally for a centrifuge, we would need significant density separations. And again, because we don't have particle liberation within the regolith, it makes it very difficult to use that type of process to actually process anything, which is unfortunate. But so definitely discrete. Centrifuges are an option and will probably be used, or at least centripetal force will be used to process things, but I wouldn't imagine a single standoff centrifuge doing too much for us, certainly initially until we've got a bit more advanced processing in place.
Good. And a question from James Sloan. There is strong interest in platinum group metals. Could you comment on platinum extraction?
Platinum group metals is an interesting one. For the most part, I imagine, so normally the way that we use platinum group metals in manufacturing on Earth is for fine like electronics and things like that. I don't foresee us needing that particularly early on. So often when people are talking about platinum group metals, we're talking about bringing it back to Earth. And so the best bet for that would probably be like asteroid mining, right? If you could find the the gold mine, right? The best thing you could probably find in an M-class asteroid would be, you know, these platinum group metals in large concentrations of them. If you could do that and bring it back to Earth, you would be a little bit rich, and then you would crash the market for a while. So probably our best bet in that terms would be to try and land the thing if we could, and then process it in situ on Earth would be easier. In terms of platinum group extraction on the moon, we don't really have, like, we need to know a lot more about the geology. As far as I'm aware, there's no significant concentrations in the lunar crust of platinum group metals. You know, we have like ppm, ppb, parts per million, parts per billion concentrations of these things, but you can't really afford to be processing those concentrations with the type of processing that we're needing to do on the moon. So we can get away with parts per million processing here on Earth, but that's because we're running at, you know, hundreds of tons per hour. If we're doing, you know, the current target for the NASA's pilot plant will be, you know, 1 to 10 tons of oxygen for a year, right? And so if we're processing parts per million platinum group metals, you're basically not actually producing anything. So will it exist in the future? Probably, but we're looking, you know, pretty far into the future.
Okay, thank you. Very interesting.
Thanks, Matt. Very good.
Pleasure. I'll stop sharing here.